Hello, welcome to lesson 17. In this lesson, we are going to look at the relationship between the critical angle C and the refractive index N. We shall also look at the applications of total internal reflection, and lastly we shall look at the determination of the refractive index of a liquid using the air cell method. Let's begin by looking at the relationship between the critical angle C and the refractive index N. Now we had derived a relationship that n sine theta, so n sine I is equal to a constant. So if you are moving from a more dense medium to a less dense medium, we can be in position to get this critical angle. So let us consider a medium like glass, that we are moving from glass to air. So we shall have n glass sine I is equal to n air sine R. So where we are choosing glass, but glass in this case Ng can be n, whereby n is the refractive index of any medium which is having a greater refractive index than air. So if we replace this Ng with n to stand for any medium apart from air, the refractive index of any medium, then we shall have n sine C, that is for the critical angle, and therefore the angle of refraction is going to be 90 and n air is going to be 1. So we shall have n sine C is equal to 1 times sine 90, because when the angle of incidence is C, the angle of refraction is going to be 90. When we make n the subject, so the sine C the subject, we shall have sine C is equal to 1 divided by n, and that's going to be the relationship between the critical angle and the refractive index n. Let's look at some example. 1. The refractive index of glass is 1.5. Find the critical angle. So we can use the formula here, this relationship, or we can go back and look at first principles. We can work from this. So let us work from this, and then we shall have n glass sine C is equal to n air sine 90, where Ng is 1.5 and n air is 1. So this will be 1 times sine 90, which is 1. And therefore we shall have 1.5 sine C is equal to 1. When we divide by 1.5, we shall have sine C is equal to 1 divided by 1.5. And if we get the arc sine of 1 over 1.5, we shall have our C as 41.8 degrees. Let's also look at this example. Find the critical angle for the ray of light moving from water of refractive index 1.33 to air. So here, the refractive index is 1.33, so n is 1.33. So we can get the critical angle using the formula. Let's use the formula this time round. If we use the formula, we shall replace or substitute n with 1.33, and we shall get this. And when we make C the subject, we shall get the arc sine of 1 over 1.33, and that will give us 40.75 degrees. Let's look at the applications of total internal reflection. There are a number of applications here. For example, we need to know that total internal reflection is responsible for the formation of mirage. It is also responsible for the formation of the rainbow. It is responsible for the transmission of light in optical fibers, and is also responsible for the transmission of the sky radio waves, and also it is responsible for the transmission of light in the prism binoculars. Let's look at the applications in the formation of mirage. So let's explain the formation of mirage. Mirage is just a virtual image of the sky, which usually appears to be like a pool of water. So we have observed this especially during a hot day when traveling, maybe using a car. We usually see this on the surface of the road. We can see the surface of the road like appearing like a pool of water in front. that pool of water is actually an image of the sky. So how does this occur is what we need to look into. So we need to know that during a hot day, the layers of air just above the ground is always hotter than the air far above the ground. So the air just above the ground is always less dense compared to the air far above the ground. So because of that, light rays from the sky is going to be moving from a more dense medium to a less dense medium, thereby undergoing refraction away from the normal. And as it undergoes refraction away from the normal, there's going to be total internal reflection occurring at a certain point. And when total internal reflection occurs, the light rays will be appearing to be coming from a certain position here, and that position, and at that point, the sky, the image of the sky is going to be seen. The virtual image of the sky is going to be seen on the ground. And that virtual image is going to appear to be like a pool of water, which is actually called mirage. Let us also look at another application here, that is in the optical fiber. An optical fiber is like a pipe, and then it is coated with another medium or with another material which is less dense than that of that pipe. So because of that, when light rays enter into that pipe, because this other layer which is being coated with is less dense, it means we shall be moving from, the light rays would be moving from a more dense to a less dense, and because of that, it will not be able to go through that other medium. So it's going to undergo total internal reflection. So the incident light is going to undergo total internal reflection in that pipe, and the different total internal reflection within the pipe is going to lead into that light coming out or emerging out of that pipe at a certain point. Whether this pipe is straight or it is bent, because of total internal reflection, we are going to have that light rays coming out of the pipe. Let's also look at this explanation for the sky radio waves. So for the sky radio waves, we need to note that for the radio signals to be transmitted from one point to another, usually the signals are transmitted from a transmitter at a certain point, and then it is sent into air, and then it can now come back to the earth where it is received by a radio receiver. So we shall have something like this. So we have a radio transmitter at A, or a station transmitter at A, station transmitter at A. So the radio waves are going to be transmitted into space, and within the space we have what we call the ionosphere. The ionosphere is also called the accretion layer. So that ionosphere has different layers. So when the waves, the radio waves, moves to the accretion layer or the ionosphere, we are going to see refraction taking place, or we are going to have refraction away from the normal. Since we are going to be moving from a more dense to a less dense medium, from more dense to less dense medium, there's going to be refraction away from the normal. And that refraction is going to further on lead to total internal reflection. So total internal reflection is going to occur in the accretion layer or in the ionosphere. And then the radio waves are going to go back to the earth. The radio waves are going to go back to the earth, and at the surface of the earth, where there is a radio receiver, the radio waves are going to be received by that radio receiver at B. They're going to be received by that radio receiver at B, and therefore this person who is at B will be able to receive the radio waves which has been transmitted by the transmitter at this station A. Let us also look at this. Now we have not explained the binatural, the prism binatural. We shall explain that later on. We shall explain that later on when you are looking at optical instruments. Let's go ahead and look at the determination of the refractive index of a liquid using the air cell method. So here we have what you call an air cell. This is an air cell. An air cell is made by getting two glass slides and you stick them together. So when they are stuck together, it always leaves a space between them, and that space is occupied by air, and that's what we call the air cell. This space here is called the air cell. So we shall get our air cell attached to a scale, the air cell attached to a scale, and then we shall place it in a beaker of water or in a beaker of a liquid whose refractive index we want to get. Remember, still that specimen liquid must be transparent. So when we place it there, normally the light rays, we shall get a monochromatic source of light which is going to produce light rays which is going to be normal. So first of all, before we rotate this, it is going to be normal. The air cell is going to be normal to this ray from the monochromatic light, and then the observer will be on the other side of the beaker. Here this is the we are just drawing the cross section of the beaker. So the observer will be at E, and then he will be observing this light through the liquid and also through the air cell. So what is going to happen is that we are going to be able to observe light. So first of all, we are going to note the position. We're going to first of all note the position of this air cell, and that position T is going to be observed and noted. So it is going to be noted, and when it has been noted, we shall note it as T1. Then we are going to rotate that air cell until when, remember, we shall be seeing the light at first. So we are going to rotate it on one side until when the light is suddenly cut off. When that light is suddenly cut off, we shall measure that angle of rotation. We shall measure that angle of rotation, and that angle of rotation is going to be measured as θ1. So after measuring it, we shall record it. Then we shall return the air cell back to its original position, that is back to that position T1. We shall return it back to that position T1, and then we shall again rotate the air cell, but this time we shall rotate in the opposite direction. We shall rotate in the opposite direction until when light is suddenly cut off again. So when the light is again cut off, we shall again measure that angle of rotation, and we shall call that angle of rotation θ2, and we shall record it. Then we shall get the average of θ1 and θ2 as theta is equal to θ1 plus θ2 divided by 2. And then the refractive index of the liquid will be calculated from NL is equal to 1 over sine C. So this method is also called the critical angle method. Reason being, when light is just cut off, that is going to be the angle of incidence will be the critical angle. So that theta is actually the critical angle. That's why we are able to get the refractive index using 1 over sine of that theta. So thank you for being part of this lesson. In the next lesson, we shall look at some examples there, and we shall see how to calculate the refractive index using the expression that we have seen there, that is NL is equal to 1 over sine theta.